Hello, this is Bruce Wallenberg once again. This is lecture 15B, the second of our lectures on interchange, pooling, brokers, and auctions. As you can see, we're going to start out talking about something called the energy broker. Think of a situation where in a state you might have, let's say, 5 electric companies. That means to set up optimal transactions, let's say, between the companies, each company would have to arrange bilateral transactions with 4 others. And there's very little chance that they could do that in an optimal way, setting up all of those transactions simultaneously. And so the results are kind of haphazard. If you want to get the best results, you have to do some sort of centralized calculation. The simplest such is an energy broker, where the companies make quotations to sell, and they also make quotations to purchase. So they say, this is what I'm willing to sell, this many megawatts at this price, this incremental price, this many megawatts at the next price. They also put in how much they're willing to pay for blocks of energy. So buying and selling, both of those quotations go in. And then the broker, as we'll see, matches them up in an optimal way to come up with the best arrangement for transfers for transactions between these companies. The Florida Energy Group broker did this as follows. Each hour, so this is an hourly calculation. And by the way, the Florida Energy Group, it wasn't a big building with dozens of staff and huge computers and big control room and so forth and lots of communications. It was a 1 or 2 computers. Maybe there was 1 person or 2 part-time to make sure it was running, and use of telephone grade communications back to each of the member companies. That was it. So it was a fairly efficient operation as far as setting it up and running it. So each member sends, now that's through these telephone grade communications, incremental costs of megawatts that they're willing to sell. So how much do I want for the megawatts I'm willing to sell? Decremental just simply means what is the cost if I'm willing to buy, how much am I willing to pay for them? So those are the bids up here. These are the 2 bids, basically sell or buy. The broker matches. Now here's the way you do it. The lowest cost seller to the highest cost buyer. If you think about that, if you want savings, you take that's the way to go. Lowest cost seller to highest cost buyer. And you keep doing that in a way. You start with the lowest cost seller, then you come up in the seller's costs. So the sellers have to be ranked at and they have to be ranked with the lowest at the bottom, and then going up in price. Whereas the buyers, pardon me, the lowest cost seller, high cost. The buyers are ranked in the opposite order. So again, lowest cost seller to highest cost buyer. And then we want to split the savings for each transaction. So if we take the FS as the selling price, FB is the buying price, then we say the cost is whatever the selling price was plus half the difference, which ends up being the average price for the two, the buy and sell. Here is an example. Here are the sellers are up here, and here are the buyers down here. Here are the incremental costs here, and here are the megawatts in this column. Here are megawatt hours if you say it's for 1 hour. here are the costs, the costs where we multiply out by the hours. And notice down here that the sellers, we put the lowest cost and then the next one, whereas with the buyers, we start down here at the bottom. We look and say that's the 45, and then we're coming. So we're going to come down here, and we're going to come up here. The net pool savings. If you just take all of this, we would add up the price of what it's going to cost. And by the way, we've set this up where we're the net for sale is 100, the net purchase is pardon me, 200, and this is 200. We set that up on purpose. If there's anything left over, it just simply either doesn't get sold or doesn't get purchased. And we take the costs here, and we say, well, how much are we willing to spend, and how much did it cost? And we get a net of 3,000. So the first transaction matches the 45 and 25 for 100. So we take this 100 right here at 25, and we match it to this 45, and we match it to 100 out of that 150. So 45 minus 25 with 100 gives us savings of 2,000. Then we take now we've got 50 left down here, so we're going to take 50 from here, and we're going to match it to this 50 down here. Let's say we'll draw the 100 and the 50. So we're going to match these two. The first one matched these two. So now when we do that match, it's 45 minus 30. They're coming together. Notice that the prices are coming together. Here's the savings. The last is to take and match. I've still got 50 up here to sell, and I match that with this other 50 here. And of course now the prices are getting very close, 35 to 30. And here is this. Now that's the end of the game. Again, if there were blocks left over in here or in here, they would just not be sold or not be purchased. And we get our 3,000 over here. This is the overall. At the end, we say, okay, well, here's the price. So they just go back and they say, okay, here are the transactions that accomplishes all of this. A sells 100 megawatts to D at this price, and so forth and so forth. And we come up with our cost figure down here. So that in the end, the broker goes back and tells them, here are the transactions. They didn't have to do it by doing telephone calls or bilateral or anything. It just went into the broker, and the broker said, do those transactions. Now, here's another big issue. Transmission capability issues. We just assumed that the brokerage scheme that we just talked about, that there was enough transmission capability. What limits the transmission capability? Well, the thermal power limit, the I squared R losses. If it gets to be too great, the line heats up and then it sags, and eventually it gets too close to the ground and causes arcing and opens the line. First contingency limits. If a line opens up someplace, then an overload can occur on a line, and now you've got thermal problems on the line. So you've got to make sure that first contingencies do not cause overloads during the transactions. Remember, we're talking about these in the presence of large transactions, and that's usually when you have problems. Transient stability. You can put a lot of power from a long over a long distance. You could do it because the transactions are very economical. Somebody's selling power really inexpensively from far away. But when you make a huge transaction, if you remember your transient stability limitations, you lose transient stability very quickly if you have a fault and lose and open a line in that system. Voltage VAR limitations, again, with large transfers, and then particularly with contingencies, you can have voltages that just get too low. Generators hit VAR limits, you're approaching a voltage collapse. Dr. Shebley did some research where he balanced and maintained the line outage probability, the loss of load probability, these are reliability measures on the system, and the expected unserved energy levels for each transaction. So you can get very, very detailed as far as the transactions and the reliability of the system. Now, we're going to talk about flow gates. We mentioned that in the security analysis and in the transmission system chapter. Flow gates. If I have a system that has 3 lines coming into it, often what I'm most interested in is the sum of the flows across that thing. So I'll draw 3 arrows, and I'll say there are the 3 lines. So the flow gate is the sum of the 3 lines. This makes it really is a very good way to approach this problem, to use flow gates. The ISO, or Independent System Operator here in the United States, other countries you would call it the Transmission Operations Center, completes a first contingency transfer analysis to identify flow gates. So you're doing first contingency transfers, and you look at and see where are the points in the system as load and as transfers go up, where are the points that start to overload. The first contingency analysis performed for what we call available transfer capability paths internal to the ISO's, what they call the market footprint. That's just the area of the system that it covers, up to 10,000 megawatts. So that's a lot of transfer. The first 3 limiting elements and their worst associated contingency with an outage. This stands for outage transfer distribution factor. Instead of line outage, we sometimes talk about instead of the power transfer distribution, we talk about outage, meaning how much power can I transfer with the worst outage in place. This is the OTDF of at least 5%. So we want to get all the ones that are significant, but some of them are very small, and we won't bother with the ones under 5%. And that's how we identify the flow gates. Now, I'm going to talk next about calculating what we call the total transfer capability. We take the power flow and we model transfers, and we just keep making the transfers bigger and bigger, and no overload should occur in the system as the transfer. So as the transfer gets to a certain level, no overloads, and no overload should occur during contingencies as well. So we've got 2 checks on it, and until we build up to the total transfer. Now this should be looking at, if you're going to use an AC power flow, then you can check voltage problems too. If you're just using linear or DC power flow, you can do a lot of this with PTDFs and LODFs for flow gates to determine this TTC values for areas and flow gates. Now, once you have that the total transfer capability, we're interested in the available transfer capability or the available flow gate. If you're looking for, let's say, what's the available transfer into an entire area, it might include many flow gates, or we can look at individual flow gates. And so the AFC, available flow gate capability, is the megawatt transfer capability on a flow gate that remains available. All right, now this is the important part. That word available means how much is there after I take everything into account that will subtract from its initial value. So it's the amount available for additional transfer of power, additional transmission service above and beyond what's committed. Now here's the committed amounts, and the capacity benefit margin is the amount of firm transmission transfer reserved by the ISO for long load serving entities. So this would be, let's say, within a city or a town that needs a certain amount of load transferred in to serve its load, and you have a contract. So they've said, okay, that's a capacity benefit. We're going to put that in. That means you can't use that much. Transmission reliability margin. How much do I have to allow extra transfers in case I have a generator outage and I need to transfer a lot of power because of that? So there's an outage. There's a margin in there to cover those kind of outages. And so we take our TTC value, and then we take off the capacity benefit margin, the transmission reliability margin, and we just put et cetera, because there are a few others, but we're not going to worry too much about all those details. These are all margins that we're going to put in. How do you use this available flow gate capacity? I'm a generator company. I've been on the telephone with some big load company, let's say big manufacturer in another state, and we've agreed that I have some energy to sell during certain hours, and the load would like to buy at that price. Now I need to determine whether I can get the power to my customer. So I make a transmission service request, or TSR, and I do that through a web page that's called the OASIS, or Open Access Same Time Information System. The transmission operator or market operator runs this. In the case in the U.S., it's the ISO. We call them the ISO. They post the available flow gate capacity on the system. So the TRS is an interchange contract defined by a point of receipt, point of delivery, and number of megawatts, and you put in the request, and the Oasis software will test it out, and it will either accept it, refuse it. It may say it's still being studied or confirmed, etc. And each one that's firm, that's been accepted, goes through an ATC or an AFC check. It goes through all of those checks, and if it passes, in other words, that amount of megawatts can be put on the system, transferred to my load, no problems, first contingencies are okay, etc. So it's been tested and it's okay, and it's scheduled. Now, this is for what we were talking about was for bilateral transfers. A spot market is a lot. We're going to discover is a lot like our brokerage scheme. The spot market, and in that loads enter bids to buy, generators enter bids to sell. Okay. So loads enter bids to buy, generators enter bids to buy. So there's, just like in the brokerage, we enter bids to buy and bids to sell. However, the spot market wants to know automatically. Remember, the energy broker didn't have any check to see if its results could be accommodated within the transmission limitations. Well, the spot market says we want to do this, and it uses an auction mechanism. These are bids, so it's going to take highest, lowest, match them up, etc. But what it does is it puts those into an optimal power flow, and the optimal power flow becomes basically the execution of an auction, and it can be used within a unit commitment to schedule generation for 24 hours out. So you'll hear what's called a day ahead commitment. That's running the OPF with the bid. So you have to enter information for bidding for load and bidding generation for every hour out to 24 hours ahead, and as well as information as to which units and how much you're going to charge for startup costs and things like that. Now, the operation with what we call price elastic loads. This is the interesting part. If you think about it, say it this way: I'm going to maximize the worth of load served, okay, minimize the cost of generation while meeting all transmission constraints. That's the other important thing. Now, since the OPF is a minimization, all I have to do to if I want to maximize something, I can minimize its negative. So I take these two and I turn it around. So if I'm going to minimize, then I take the cost of generation. Here's our old sum over all the generation. Actually, these are bids. These are what were bid. This is the cost of the load, the bids to sell, and these are the worth functions for the loads. So here's the generation here, and here's the load. That probably doesn't look too much like the word load here. So here's the load, and the W function is the load worth. How much is it worth? This is really the bidding function that the load says, this is what I'm willing to pay for so many blocks of megawatts. So I'm minimizing this F gen minus W load, and of course I have to match. So there's a constraint on here. I have to match the generation to the load. So if we take our Lagrangian function, we say I'm minimizing F minus W, and then I have the Lagrange for basic generation minus load. Obviously, there are also min and max limits that have to be added to this, as well as transmission limits, as well as security constraints. But let's just go with what we've got right now. So we take the derivative with respect to the gen and with respect to the load. We get these equations here, and we simply discover that these derivatives are the supply price curve and the demand price curve, with the result that we want them to be equal to each other. Now, if you've ever had basic economics, of course, you know that there's a demand and there's a supply, and if you look at it, we usually say that the demand curve is decreasing. I'm not willing to pay as much for larger and larger amounts of power as much as I would for smaller amounts. Similarly, the generation says if you just want a little bit, it's very low price, and then the price goes up, and where they cross over right here is the clearing price. Oftentimes these curves, we drew it here as two straight lines. Sometimes the demand curve curves down like that. Generation, as we know, will always curve up like that. Again, it's just where they cross. And that crossover point says that's the point where I'm going to charge for a certain amount of power, and I'm going to charge a price which the load, which the demand, is willing to pay for that same amount of power. And that's what the optimal power flow does, but it does so meeting transmission constraints, voltage constraints, and security constraints. So here's an example. We say the F have the ABC coefficients that are up here, and then here are the loads down here. Let me draw a line across here, and the loads, these loads coefficients for our functions are our A, B, C capitals down here. The loads are each 100. This is our 6-bus system. Okay, this is our 6-bus system. Here are the ABC and the P-min and P-max. And what we're going to do first is we're going to do it with no line limits. This is supposed to be N. This is supposed to be line. Pardon me. No line limits. So I'm ignoring transmission limits. This is with a DC power flow, and we know that in that case all of the bus lambdas or the locational marginal prices are equal. There's no losses, and we supplied all of the loads. If I now go in and I say line 24 and 36 are going to be held to their limit of 60 megawatts, now I get different values of lambda at the different buses, and the optimal solution says I couldn't supply all the load at bus 4 or bus 6. I had to shed some load in order to meet these conditions. And so this is the kind of thing that happens. It says if I can't meet the load and still meet the transmission conditions. So the so-called bus lambdas or LMPs, the lambdas are prices at each bus called the locational marginal price. The generators are paid the LMP. The loads pay the LMP. So the market operator collects the payments from the loads and pays that to the generators. Now, if all the LMPs are identical, then the amount collected is equal to the amount sold, and there's no surplus. But if there is congestion, then the lambdas differ, and there will be a surplus. The market operator will collect more than has to be paid out, and the surplus is used to pay what are called financial transmission rights, FTR payments, which are, I like to say, insurance payments for people that want to use the transmission system. So an independent generator can purchase an FTR as an insurance policy against the possibility that the transmission system will be overloaded. Recommend the course that's on the same system here, the CUSP web page, the course by Ross Baldick from University of Texas, which goes into these kind of things with much greater detail. Last of all, we run what's called a security constrained unit commitment. So bids from generation and load for the next 24-hour period starting at midnight the next day are collected. So let's say at 2 o'clock in the afternoon you have to submit your bids for the next day, and you have to submit bids for each of the 24 hours and tell them when you're willing to let your units be put on and so forth. The unit commitment uses a security constrained optimal power flow within the unit commitment to dispatch generation. So it comes out with a generation schedule. So the result down here is a unit commitment schedule for the 24 hours. It gets the LMP value for each hour, and it meets the security limitations of the network. And that is what is used. And there are various adjustments made on top of that to take account of differences in the predicted load and things like that. Thank you very much.